Hello and welcome back. Finally Lindström's theorem is over and we can start a new chapter. In this video I'll talk about fluid statics and more specifically pressure variation. So let me just define fluid statics in short terms. In fluid statics there's no relative motion between fluid particles, so there are no shear stresses present. This does not mean that the fluid particles are not moving, but only that they are not moving relative to one another. If they are moving, as in a can of water rotating about its axis, they move as a solid body. The only stress involved in fluid statics is the normal stress, the pressure. It is the pressure acting over area that gives rise to the force. So what is pressure variation then? Well, pressure is a quantity that acts at a point, we all know that, but does it have the same magnitude in all directions at a point? The answer to this question I'll show you later, but a pressure P is assumed to act on the hypotenuse and different pressures Px and Py on the other two sides of the infinitesimal element, which has a uniform depth dz into the paper. So let me just draw what I just said. So we have the y-axis, the hypotenuse, ds. We have a force, or pressure, whatever you want to call it, and its different components, you can say. Denoted by subscript x and y. You also have angle, say beta. This side is the x, this is the y, this is the s. We have a downward pressure, you can say. Where this is rho. And this is the x-axis. The fluid particle occupying the fluid element could be accelerating, so we apply Newton's second law in both the x and y directions. So the sum of the forces in the x direction is going to equal max by Newton's law. Similarly, the summation of all the forces in the y direction is equal to may. What does this say? Well, this is going to be equal to px dy dz minus p ds dz sine beta. It's quite obvious. And this is going to be equal to rho dx dy dz over 2ax. Same holds for our other summation. This represents py x dz minus p ds dz, now cosine beta, well, minus rho g dx dy dz over 2 is equal to rho dx dy dz over 2 ay. Recognizing that dv, let me see, dv is equal to dx dy dz over 2. We have that dy is equal to ds sine beta and the x is equal to ds cosine beta. substitute these into our equation, and we will obtain that px minus p is equal to rho over 2 ax dx, and py minus p is equal to rho over 2 ay plus g dy. Here we see that the quantities on the right hand sides of the equations are infinitesimal multiplied by the x and the y, and can be neglected. So that is px equals py equals p. And if you're wondering about this strange v, it's really that we tend to use this special symbol to represent volume, and v to represent velocity. It's just to hold them apart, really. I just redrawn this triangle, and I think I said this was the pressure, but what I really meant was it's the weight, sorry for that. But since the angle beta is arbitrary, this holds for all angles. We could have selected dimensions dx and dz and arrived at px equals pz equals p. So in our applications to fluid statics, the pressure is a scalar function that acts equally in all directions at the point. But how does pressure vary from point to point? The fluid element of depth dy in this picture is assumed to be accelerating. Newton's second law provides that p dy dz minus p plus the partial derivative of p with respect to x dx dy dz equals rho g dx dy dz ax. Similarly, p dx dy minus p plus the partial derivative of p with respect to z dz dx dy equals minus p g dx dy dz plus rho dx dy dz. Sorry for this. Az. If the element were shown in the y direction also, the y component equation would be p dx dz minus p plus the partial derivative of p with respect to y dy dx dz equals rho g dx dy dz ay. These three equations reduce to that the partial derivative of p with respect to x equals minus rho ax. The partial derivative of p with respect to... Sorry, my camera died. But the partial derivative of p with respect to y equals minus rho ay, and the partial derivative of p with respect to z equals minus rho times az plus g. I'm drawing a new figure, and this represents the forces acting on an element of fluid, basically. It's basically what I just said, but in picture. So finally, the pressure differential can be written as dp equals the partial derivative of p with respect to x dx plus the partial derivative of p with respect to y dy plus the partial derivative of p with respect to z dz equals minus rho ax dx plus, minus rho ay dy plus I'm so sorry, minus rho az plus g dz. This can be integrated to give the desired difference in pressure between specified points in a fluid. In a fluid at rest, there is no acceleration, so the pressure variation from our equation becomes dp equals minus rho g dz, or dp equals minus gamma dz. This implies that as the elevation z increases, the pressure decreases, a fact that we are aware of in nature. If gamma is constant, then our equation allows us to write that delta p equals minus gamma delta z, where delta p is the pressure change over the elevation change delta z. If we desire an expression for the pressure, a distance h allow a free surface, the surface is 0 on a free surface, it would be that P equals gamma h, where h is equal to minus delta z. Our equation is used to convert pressure to an equivalent height of a liquid. Atmospheric pressure is often expressed as millimeter of mercury. The pressure at the bottom of a 30-in column of mercury is the same as the pressure at the Earth's surface due to the entire atmosphere. If the pressure variation in the atmosphere is desired, a last equation, or actually this equation, would be used with the ideal gas law, namely that I can write here, I think, that P equals rho RT, to give that dP equals minus P over RT G dz, or the integral from P naught to P dP over P, which is equal to minus G over R times the integral from 0 to Z of dz over T, where P naught is the pressure at Z equals to 0. If the temperature could be assumed constant over the elevation change, this could be integrated to obtain P equals P naught times e to the minus g z over RT. In the troposphere, for example, between the Earth's surface and an elevation of about 10 kilometers, I think, the temperature in kelvins is T equals to 288 minus 0.0065 Z. And our equation could be integrated to give the pressure variation. Yeah. Thank you for watching. Have a nice day.